Hello community, so great that you're back. We have a brand new study about DPO. So if you use DPO here in reinforcement learning, careful. Let me explain why. Brand new paper here from Princeton University and University of Illinois. And they have here July 10th, 2025. A brand new paper, Is Your Language Model a Poor Implicit Reward Model? Now, there's something special about this paper, and if you have a look, you will see it is a beautiful paper, but it is not easy. I have my problems understanding here the deeper configuration that they are going to prove, so be prepared if you have a look here at the pages. It is not the easiest. Now, it is today the first day that it was published, so I can give you here, if you want, my main insight, and maybe it help you if you read the paper, that you already have here a start. Now, imagine you're tuning here your language model, a Llama GPT model, and you want it more helpful, more aligned to your values, more in line with your corporate strategy, whatever, what we do, could go with a supervised fine-tuning, but now we have a reward model for reinforcement learning. Great. So what we do, we take here a pre-trained LLM, we have here a reward model that we train on our values with our dataset. And this is an explicit reward model here. And then we use both here. We use this reward model here. It provides the reward. And then we have a fine-tuned LLM that includes here our values, our ethicals, whatever you want. But we have a second option. And of course, the simplest one is DPO. Yeah? Now, DPO is simple, a breakthrough. It is an implicit reward model, and its reward function is defined directly by the log probabilities it assigns to a response relative to a reference model. So you see, we do not need another LLM as here an RM. And this was beautiful. But now we discover, oh my goodness, it has some major disadvantages. Now, it started all again here with reinforcement learning here by OpenAI, and then here, this is the original DPO paper. If you have not seen my videos, I have multiple videos on this. But what they are doing is almost identical. They are trained on the same data, on the same loss function, on the same language model, pi sub theta, and they differ only in one minimum thing, and this is how the reward is computed based on the policy. Could this be it? Because if we look at this, you say, okay, so we have my prompt X, I have the system response Y, I have my language model pi sub theta, and then the explicit reward model, this classical OpenAI, reinforcement learning by human feedback, we just add here another layer on our transformer architecture. We have a linear head over the hidden representation. So we can combine here the latest hidden representation vectors here with a matrix to get a scalar. In the implicit reward model, things are different. We don't have this reference. We don't have here another architectural chains. We have a reference model that we are referring to, and normally this reference model is just our pre-trained model without any fine-tuning. And yes, this is really different. So let's say you have your prompt X, you respond Y, language model backbone P sub theta. Now, the explicit reward model computes the reward by looking at the meaning of the entire response, encapsulated really in its final hidden layer representation where everything is already calculated. However, in the implicit reward model, this is central to the DPO mechanism and all the other DPO derivatives, it is defining here in a simplistic version the reward based on how much the fine-tuned policy prefers the response Y compared to a fixed reference policy model pi reference, usually the original pre-trained model. So we do have really two models, but it is just in different stages of, let's say, development, of evolvement. So let's go even closer. Let's say this explicit reward model processes now my human prompt and generates a prompt to produce here the final state vector. This is H for the hidden state vector. Then we apply here, as I showed you, a new trainable linear head, we call it U, is applied here to this vector representation that we extract from the final hidden layer state vectors, and we want to produce a scalar reward. So easy, né? You know this formula, simple multiplication. Now, in the implicit case, it is more complicated. No? We don't use here an architectural change. That's why it's so simple. No? But if you want, the analogon to the additional head is now the model's own log probability calculation that goes with the standard formula of DPO. Now, everything was fine until this paper emerged, and this is here, all roads lead to likelihood, the value of reinforcement learning and fine-tuning. And what they showed us here, among other papers, this is just the reference I personally recommend, and they say despite a vast similarity of the explicit and implicit reward models, we found here with prior works that the implicit reward model tend to generalize worse, especially out of distribution. So careful, this is now talking about out of distribution data and the generalization to new unseen data, to new scientific terms, to new financial technical terms, to new macromolecular names of compounds. So whatever is new, your implicit tends to have here less accuracy in ranking here the candidate response. And they say this existence of a generalization gap here between IM and explicit is puzzling. Why would such a tiny little difference, how the reward is calculated, have such a massive effect here in the end result? Now, I think you should know these three things. The first is if you have a sequence model pi theta, it assigns a probability to a sequence, an output sequence y, y1 to yt, given here a particular input x. By the chain rule of probability, we can write this in a very nice format, where in a transformer-based LLM, we have at each position t, the model computes here the hidden state. This is projected to the logit for the vocabulary via an unembedding matrix U. I showed you this with the head. And then we simply have a softmax operation over the logit to yield to the probability distribution. The second thing you must know is the Bradley-Terry model. This here is, if you want, for the pairwise competition, and it is a beautiful simplification. So what we have a pairwise probability. We are given a pair of answer. And let's say we have a good answer, this is y plus, and we have a not so preferred answer, this is a y minus. And we can now define, if you want, the probability that y plus is preferred in a very simple equation. We can then have a look at the loss function. So we take the negatively log likelihood, we minimize the loss function, and this simply pushes here the reward for the positive answer that we are looking to enhance, and it reduces or we move away on the gradient on the hyperplane here from an answer that we do not prefer. So over the set of the labeled preferences, we have now a form here of a very specific, this is the Bradley-Terry form of the loss function in a simplified model. Now, we will use this because the next step is, of course, because R is parameterized by some weights here, theta of the models, we can now compute the gradients. This is here our gradient computation here of our loss function as you have it here. So therefore, yes, a little bit here of mathematics, and then in a gradient descent update, we get a relatively simple version here. So you see, if we upweight here the parameter influencing here the reward function on the positive answer by a factor of this, and we downweight here those influencing here of the negative component by this factor. Great. Now, you know, because R is here a differentiable neural network, the gradients of L with respect to its parameter flow back and adjust so that the average across many pairs, that the preferred response get higher scores and the dispreferred, the Y minus, gets lower scores. Easy. Just let me give an example. You have a prompt X and I ask my machine, hey, explain why the sky is blue. No? And my preferred answer would be, my reinforcement learning by human preferences, Y plus, because molecules scatter shortwave length sunlight more than the long wavelength, and Y minus, because it's painted blue by nature. So what do we do? Or what is the mechanism that we look at? No? The reward model might now, after training, assign now here different rewards scalars here to my answer. So here the reward for Y plus, what I like, is 1.2. And the reward here for Y minus, the answer that I do not prefer, is much lower. So therefore, if I calculate now the probability here of my preferred answer, the sigma here is about 0.69. Then if I do calculate here with the Bradley formula here the loss, it is about 0.37. So therefore, if we have now our gradient steps, we now increase towards here the positive answer with the reward, and we will decrease here the negative answer. Now, knowing these basic tools, we can now look at the generalization gap that we encountered here. Let's have a look. So as I told you, almost identical training between here the implicit reward models and the explicit reward models. We see here, especially here under the token level shift paraphrasing translation, that the implicit models underperform the explicit models. How is this possible? Well, if you use DPO, your implicit model here, and it is failing in some crazy ways, no? This paper now gives you here a primary suspect, because it explains to you in detail that what you're doing in the training in the DPO-tuned models is simply overfitting your model to superficial token patterns in your preference data. But your DPO model is not learning what you want the model to learn. So there's an inherent training regime difference that is massive. How is this possible? Now, the beauty of the approach by the authors is, yes, there's a complete theory. I just zoom in on the most important part, that if you look here at a single gradient step, the delta R, how does it change the reward for a new pair X bar, Y bar? Now, in the explicit reward model update, they show you that this is here the mathematical form, and you see here the dependence in this formula is simply only on the hidden representation H here. However, if we do the same now for the implicit, the authors tell us after some pages of a little bit of mathematics that this would be the expression. And now have a look at this. There is now this absolutely fascinating term we have to have a closer look, because if you want to understand what this term is, you will find this here is defined here in this particular way. Now look at this, you see you do not have here a dependence only on the semantics, on the hidden representation H, but suddenly you have on exact token matches between the new answer and the other answers. And you say, why the hell suddenly you have an exact token match in this term? I will explain it in 2 to 3 minutes. But just to tell you, this was the idea, single gradient step, calculated here, explicit, implicit, find out explicit, goes only here for the semantic complexity, beautiful. Implicit, oh, we have here exact token matches, and this is never a good idea in any AI system. So if the token here of the unseen response Y bar is the exact same as the token in the good response Y plus, then our row is positive. Great. But if it is different, although it might be semantically similar, this term can become negative. And this is what we call a catastrophic implication, because now the implicit reward model is biased to a reward token overlap function, and you don't want this. So here this implicit reward model struggles massively to generalize to semantically similar responses if they use only different words. And now you see the sensitivity just comes in by the training data. Let's have this again. So the authors now show, and this is if you want the summary of the complete paper, if you have the explicit reward models trained here by gradient descent, behave like a logistic regression on the semantic features here of the hidden layers, and provable, generalized to any unseen token that aligns well in the representation space. So this model here, this reinforcement learning by human feedback, is doing great. It learns here new technical terms. It generalizes here to more complex structures. It simply works better. However, in the implicit model, suddenly we have with this term that I showed you in the single reward update, we have now this overlap that will crush here the performance in our training. So this reliance here of the implicit reward models on the exact token makes them extreme brittle to some surface changes, while here the explicit reward model can go with a deeper semantic structure and explore here the meaning of your new training data. Let me give you an example. Very easy. So let's say in your training pair, there was some knowledge, some information. Let's say UI plus was the cat sat on the mat. Beautiful, highly intelligent, I know. And then to generalize this to unseen data, we need now a new query. This is Y bar, yeah? And now instead of cat, I use the term feline, and instead of mat, I use the term rug, and instead of the term sat on, I say now rested upon. So you see, as a human, you immediately understand the semantic context is identical, but the tokens for the AI are completely different. The tokenizers assign completely different tokens to this, and this has consequences. Because no token in Y bar matches now any token in Y plus exactly. So this means if we have here an implicit model, this implicit model never learns to reward this paraphrase here. And now we understand the difference between implicit and explicit reward models. If you want to see this on a deeper mathematical level, again, here we have our row formulas here. And you see here the very first term is already what is the critical factor, if you want. Yeah? This is one if the tokens are exactly identical. Can you imagine this AI system is now really going into its tokenize and really checking here the exact token? So if this leading term here, the indicator, if they're not equal, the indicator is 0 and the remaining terms tend to cancel out or be very small. So if we have an exact match case, so if it's really here on your pre-trained data, you have no other word, no new scientific term, no new innovative term, no new marketing term. If everything is staying absolutely 100% in your vocabulary, okay, then it will contribute here in the training with a non-zero gradient term, then it will have here an effect if you train your model on reinforcement learning. But if you do not have that the tokens absolutely align in exact match cases, this terms becomes more or less 0, and the corrective probabilities that come later here nearly cancel out, so there is no contribution at all, so there's no learning happening. So again, now in more details what we just discussed already, because here the gradient in this particular case only activates when the tokens line up perfectly with those tokens seen during the training, then, so if you paraphrase Y plus, so that none of the words match literally, this row becomes 0. And the update here in the reward step is essentially 0. No learning happening, no reinforcement learning, DPO is dead. What a beautiful insight in this paper. But I have to tell you, the paper is mathematically not trivial that you say, I just read it here, walking a little bit. So take your time, cup of coffee, find a nice nook, take 2-3 hours time and have a look at the paper. Yeah, and they show us here this explicit reward model update here has, of course, this form, and you see here, this is the inner product here of continuous vectors. We are operating here into a vector space. So this means here that it is still learning the semantic similarity of similar hidden states. Therefore, the model will still learn an appropriate reward, even if we have new technical terms, new innovative terms, new marketing terms. If you want to see this here in my very dedicated visual interpretation, we're in a vector space. We have a vector to here, this point that is cat. And you see in an epsilon environment very close by, because we're in a vector space, we have everything from feline, kitty, pussycat, whatever you call your cat, maybe all the different names. So whatever you use now in a new technical term, a new marketing term, it is all here already in the similarity close by, and the AI system has no problem to understand, those are almost exchangeable terms, so I can use here this update here of the single rewards tab. And if it's nothing here, maybe it's just looking, okay, there's a kind of a similarity with dog, whatever. So this explicit reinforcement learning of reinforcement learning by human feedback works. They collected, the authors, a lot of experimental data. Please have a look. I have to refer you to the paper. I just tell you the result. Whenever there are token level shifts, so whenever you use the word car, or you use the technical term automobile, you will have a significant difference in the performance of the system. On token level shifts, whenever they happen in this AI system, the explicit reward model consistently and massively outperforms all other implicit reward models, and we just went through why this is the case. And if this model is faced with paraphrased or translated responses, even this, the implicit reward model plummet here in the performance, sometimes to near random chance, so it becomes unworkable. While, on the other hand, our explicit reward model, reinforcement learning by human feedback, is still robust. And this experimental data, have a look at the paper, confirms the theory. Love it. Prime summary, explicit, semantic representation, it works, check. Implicit, heavily biased towards superficial token level overlap, not recommended. If you use DPO, be really aware that you might just be overfitting here to a very specific vocabulary of your preference dataset, and you're not learning new stuff and you're not realigning your model to your training data. The resulting model might be not what you expect. So yeah, AI can fall if you're not careful and you understand and have read this beautiful new paper here that DPO is not as perfect as we thought. We discovered there are some massive implications. If you use DPO, you have to be extra careful. And interestingly, the old models, the old reinforcement learning by human feedback still work. What an amazing world. If you want to see more, subscribe. I see you.